All right, so everything on the top is all the same. Let's quiet down, please. Looks like we've only got about half of the class here now anyway. Weather's getting too nice outside. Okay, let's quiet down, please. All right, so we are just finishing up our chapter on amines. All right, and we'll be able to finish, I think, most of that today. On Monday, which will be our last day of class, we will do some kind of reviewing. I'm not sure what topic is the best. We could do a few structure determination problems or some synthesis or something like that. There's not enough time for me to rehash everything we've learned in this class. So we'll do something like that. Okay, let's quiet down. We have already talked a few things about amines. We've talked about their bonding, how to name them, their physical properties, how to make amines. We learned a couple of new reactions on ways to make amines. And then we talked about acid-base chemistry. And we listed out a bunch of amines. We found out that the aromatic amines are less basic than the aliphatic amines because in general there's some resonance going on or hybridization effects, things like that. And so what we're going to finish off on are some different reactions of amines. Okay? I added in one slide. We're just going to review a few reactions of amines that we've seen before, and then we're going to focus kind of on a new type of reaction, and these are reactions of anilines. Okay? And so this will turn into mostly aromatic chemistry again, but it will allow us to do a few things that we haven't been able to do up to now. Okay? We're not going to go, when we get to that, I'm going to basically show you the reactions and we can use them to predict products or to do synthesis, but there's a few kind of lengthy mechanisms involved in that chemistry and we're not going to spend the time going over that. I think we've had unless you guys disagree, I think we've had enough mechanisms at this point. You agree? Okay. All right, and then we'll take those reactions and all the reactions we've done and we'll apply it to some syntheses as well. Okay? Any questions? All right, let's do a clicker. All right, so let's start out. Reminding ourselves of some reactions. And particularly, we're going to start out reminding ourselves about how amines can function as nucleophiles. All right, so I added in this slide, but this is just a couple of examples of amines acting as nucleophiles. All right, so these are related, the top two are related to the reaction we just saw on the clicker question, but they don't have the reduction part of it. All right? So if we take a primary amine and we have a ketone, we end up essentially substituting the nitrogen for the oxygen, and oxygen is lost as a water molecule, and that water molecule is made up of these atoms right here. Okay? So all we really have to do to draw the product then is just connect these two together. We're going to put the nitrogen there, and then we add the alkyl group, like this. Okay, so it's going to be the neutral product, and so there's not going to be an extra H on there or anything. Of course, for this, and so what kind of a functional group is this called? An imine. Of course, this imine could have essentially either an E or Z configuration or stereochemistry, but we're not going to worry about it. I drew it this way because I put the alkyl group on the nitrogen to the side of the smaller alkyl group that was part of the ketone. Okay, so it would be probably controlled by the steric hindrance there. All right, so that's an imine. If we do the reaction between a secondary amine and either a ketone or an aldehyde, we get a slightly different product. Okay, so the same type of thing is going to happen, but in the end, when we went over the mechanism before, we end up losing a different hydrogen, right? We only have one hydrogen on the nitrogen to lose to make our water molecule. So where does the other hydrogen come from? From the alpha carbon, all right? That's going to be the most acidic one, so we're going to have this. We have our two oops, I did that wrong though. Well, let's go ahead and draw the two steps here. Okay, so we would get to an intermediate that looks like this, right? This is just like the imine, but in order to get a neutral product, we're going to have probably the amine acting as a base, like this, and it's going to remove one of these alpha protons, like this. These electrons can go here, and the electrons can go up on the nitrogen. Okay, so what we get out of that is a single bond to the nitrogen now, but a double bond to the carbon. Okay, and so instead of an imine, this has a double bond, so it's called an enamine. Right, enamine. We didn't go into this chemistry, but enamines can essentially do alkylation reactions like ketones and aldehydes can. All right, so you might imagine that we have this nitrogen here with non-bonding electrons. If these electrons come down to reform the nitrogen-carbon double bond, we can use this pi bond to react with an alkyl halide. Okay, so that kind of chemistry can be done too, but that's just beyond the scope of what we're covering. All right, the last example that I put up here is the reaction of an amine with a carboxylic acid derivative, right? So I just chose the most reactive one here. Usually when we do this, we have to have an excess, or we use two equivalents of the amine, and all we end up doing is a acyl substitution reaction, right? So this is going to go like this. We're going to end up with NH there, and the amide. All right, the other byproduct, the reason that we use that second equivalent of the amine is because in the process of this, we're going to lose an H off the nitrogen and the Cl, so we've generated hydrochloric acid, and if we don't add that second equivalent of base, then we'll start protonating our amine to form the ammonium ion, and that won't function as a nucleophile anymore, right? So our other byproduct, if we want to draw it, would be this ammonium ion here. So it's essentially neutralized the hydrochloric acid that's been formed. Okay, we could do this same reaction with anhydrides. We've seen we can do them even with esters to go to amides, and so these are just all the nucleophilic acyl substitution reactions. Okay, so these are just kind of, and then of course we talked about alkylations, but adding alkyl groups to amines, but the problem is that it can over-alkylate. It can always go to the ammonium ion. We looked at what was called the Gabriel synthesis as a way to get around that. Okay, so that's all as being nucleophiles. So let's look at anilines. Okay, so from the reactions that we know already, and we're going to focus now on the chemistry of the benzene ring. So we're going to step back and review some chemistry that we learned earlier. Right? And so we know that this amine, so the amine on the benzene ring can function to modify or influence the reactivity of the benzene ring, right? So that amine, what would we consider it? Is it an activating group or a deactivating group? Right? It's a strong activating group, right? Right? Because the non-bonding electrons on the nitrogen can be donated through resonance into the ring. As we increase the electron density in the ring, that makes the benzene ring a stronger nucleophile. Okay? And what about directing? What kind of directing does it do? Ortho-para-directing, like all of the other activating groups. All right, so we could do reactions like we could say brominate this, and if you add iron bromide, right? So this is an ortho-para director, but remember that with these strong activating groups, if we use the catalyst, we end up brominating all of the ortho and para positions. Okay, so we get a bromine here, and a bromine over here. All right, if we want to do it just one time, then we can just add Br2, and this ring is so activated we don't even need the catalyst. Okay, and so in that case we would just get a mixture of ortho and para. All right, we could get one here plus one over here. Okay? So, what if we want to, say, add an alkyl group onto this ring? So can we do this? Let's just maybe add an ethyl group on here, an aluminum trichloride, to give a mixture of the ortho plus the para ethyl anilines. Does that work fine? No, there was a problem with this. Okay? And so in fact this doesn't work. And the reason for it was that the amine coordinates with the Lewis acid, with the aluminum trichloride, and it gets something like this. So NH2, and this is essentially kind of bonded to the aluminum trichloride. That puts a minus on the aluminum and a plus on the nitrogen. And whenever we have a plus on the nitrogen right next to the ring, that makes it into a strong deactivating group. So it completely switches its effect on the benzene ring. Okay? So the reason I'm going through all of this is we have learned some chemistry, not in this chapter, but maybe in the last chapter, or one of these last chapters, I got them all mixed up, that helps us to get around this problem. Okay? And the way that we can do that is that we can react this, let's say we react it with acetyl chloride. Okay? And maybe just so we don't have to use two equivalents of the aniline, we'll add something like some pyridine or something like that, another base that can neutralize the hydrochloric acid. And this, instead of a reaction of the benzene ring, is an acyl substitution reaction. So we essentially put it's called an acetate group on the nitrogen. Okay? So now that we have this amide, is that amide, is it an activating group or a deactivating group? Right, it's still an activating group. It can donate this way, but it also shares its electrons with the carbonyl group. Okay, so it's a weaker activating group. Okay, so this is a weaker activating. And in fact, because it's a weaker activating group, if we now try to do the Friedel-Crafts reaction, it won't coordinate the aluminum trichloride. Okay? So it's not really what, in some ways it's kind of like a protecting group, but it's more like a modifying group. So it modifies the reactivity. So now, if we want to do this Friedel-Crafts reaction, okay, now this will work. Right? So let's say we want, let's say we're going to get both of these. Maybe we want just the para though. Let's imagine that. And so we'd have to get this mixture and then we'd separate these, okay, to get the one we want. And then if we want the amine back, we just have to hydrolyze the amide. Okay, and so we can hydrolyze that either under acidic or basic conditions. Let's just hydrolyze this with base, H2O, and so then we free up the amine. This, and plus, of course, we'd get the acetate as our other product. We're in base, so it's going to be as its conjugate base. And so now we have essentially done what we tried to do up here. But we did it by affecting the reactivity of the amine. We put on a group, we made it a less activating group, so it doesn't react with the aluminum trichloride. We can now do our Friedel-Crafts alkylation, or we could do an acylation, and then we just remove that group. Okay, so this is a way to get around the problem we had before. All right? I know you guys were just wishing you had a way to get around that all this time. All right, so let's look at another reaction. Okay, and this is the one that has a whole bunch of steps in the mechanism, but we're not going to really go through all those reactions. And so what we do is we take aniline, we react it with, essentially with these two together, this is nitrous acid, right? It protonates the nitrogen there. And so it's going to, the nitrogen's going to end up being connected, and we get this compound over here that's kind of interesting because it essentially has this N2 group attached, and this is called a Diazonium salt. Okay? You can make diazonium salts of alkyl groups too, but they're super unstable and they're not very useful. Okay? So, and even this diazonium salt on the benzene ring, we have to keep it cold at like 0 degrees in order to keep it under control. All right, and the reason why we do this is because you might be able to imagine that this N2 group is a very good leaving group. Right? Because N2, right, the gas that's in the air and everything is super stable, so it makes it a very good leaving group. All right, so it allows us to do kind of substitution reactions on benzene rings in a way that we haven't done before. All right? I'm not sure that all of the mechanisms for the actual substitution reaction are known, whether it's more of a radical or whether it's an actual you can't really do SN2, but we can end up converting an aniline into something else. And some of them are just things that we already know how to do, but some of them are kind of interesting that we haven't been able to do before. So we're just going to make a little tree around here. There's a series of reactions using copper halides. So we can use copper bromide, copper chloride, or we can actually use not just halides, we could use copper cyanide. And in each of these cases, whatever is attached to the copper substitutes for the N2 group. Okay, so this is another way. You know, we already know how to do a bromination, so at least if we're just doing it in this sense right here, it doesn't seem to offer a huge advantage. But I'll show you there is some things that it allows us to do. Okay, we can put the chloride, we can actually put a nitrile on the ring in this way. Okay. We can also substitute if we just use like sodium iodide, we can put an iodide on the ring. You know, in each of these cases, N2 would be the leaving group, and you know, we just bubble away or whatever. All right, so there's some other interesting things that we can do here, though. If we just react this with water, then what happens is we substitute the diazonium compound and we put an OH on the ring. All right, so this is a way we can make a phenol. And the last one I'm going to put on here, there's a way to put a fluorine on there, but I'm not going to ask you how to do that anyway, so there's no sense in packing that in your brain. The last one is we can use this hypophosphorus acid, if I got that right. And this seems kind of dumb in the first place, but I'll show you an application in just a second. This essentially just replaces that diazonium solid, the nitrogen with a hydrogen. Okay? So, you know, we could do this interesting synthesis from like benzene. We could do a nitration to make nitrobenzene. We could reduce that to an amine. We could make the diazonium compound. And then we could react that with this acid and we could make benzene from benzene. Right? Wouldn't that be useful? All right, so these are just some new reactions that we can then put into synthesis. One thing that's kind of interesting process is, let's just sneak this in down here at the bottom. So essentially we're starting, well, let's step back one more step. So usually to form an aniline, we would start with a nitro group. Okay? We can do a nitration reaction. We know how to put that on the ring. So nitro groups are deactivating, meta-directing, right? If we want, we can convert this. We can use, say, hydrogen and palladium on carbon, or that tin, or what was the other one? Iron and hydrochloric acid. We could reduce that to an amine, to aniline. And in this process, we have converted this deactivating group into a strong activating group. All right, this is activating. And so we can modify, if we're going through this process, we can put different groups on the ring with these. We can use nitro group to be a meta-director, and then we can convert it to an aniline, which is now an orthopara, and it gives us lots of options on where to put groups onto the ring. Okay, so let's utilize this. All right, so these compounds we're going to synthesize from benzene. All right, so let's look at that first. What would it be? 1,3,5-trichlorobenzene. So think about, up to now, how would we synthesize that? Right? What's the problem? What's the issue? Yeah, all of those halogens, the chlorine is an orthoparadirector. Right? So if we put on one, we can't get the other ones meta to the chlorine. All right? Because they're all orthoparadirectors. So how do we do this then? And so what we're going to do is we are going to use the chemistry we just learned about to control this. All right? So, yeah.
If we were to put a nitro group on benzene and then turn it into anilines and then use chlorine and a catalyst, could you put all of those on?
Yeah, so that's exactly right. So that what the suggestion was, we start with benzene, right? And we first put a nitro group on, just like we talked about. So we use nitric acid and sulfuric acid as a catalyst. Set up this epic battle, remember, of these two acids to see which one has to act as a base. And we add the nitro group. Okay, so what do you think? So there was one suggestion, I'll follow that up in a minute. Could we, this is a question, could we chlorinate this one, FbCl3, could we do this 2 times to put 2 of the chlorines meta to the nitro group? No, why not? It is deactivating. We can still halogenate, though, with a deactivating group. But there's a problem. Right. So the problem is that when we put on the first chlorine, whatever is the stronger activating group is going to be the one that controls the position of the third group. Okay? So it's not that the nitro group will continue to be the directing group. And so here, let's even break this down. If we went to here and we tried to chlorinate this again, then the problem is that this is the orthoparad group. It's still a little bit deactivating, but not as deactivating as the nitro group. And so that's the one that's going to control where the second chlorine goes. Okay, so because of that, this direction won't actually work. So the better direction is what was suggested is we're going to reduce this. Okay, so let's just use H2 palladium on carbon. I don't know if I'm going to have enough room in here. So we go to NH2. Then we've seen, and we already talked about it today, that if we chlorinate this with a catalyst, we can chlorinate all of the ortho and para positions, both ortho and the para position. Okay, so then we use Cl2, FeCl3, and it goes to here. All right, so now we have all the chlorines on there. Yeah, Kristen.
Would we have to make the nitrogen less activating so it wouldn't complex with the iron?
Okay, so good question. So the question is, do we have to go through this amide? Do we have to modify the reactivity of the aniline, of the nitrogen, in order to do this reaction? It turns out we don't, and I think the reason is that iron trichloride is a weaker Lewis acid than aluminum trichloride. And so the iron won't coordinate the nitrogen and cause problems like the aluminum trichloride would. Okay, so we don't have to do that here. All right, so now we've got all the chlorines on the ring, and essentially what we need to do is just remove the nitrogen. Okay, so then we can use NaNO2 and hydrochloric acid at 0 degrees, makes the diazonium salt, plus with the chloride counter ion with all the Cl's. And then we use this H3PO2. It just protonates or adds a hydrogen there. So, I was joking about converting benzene back to benzene, right? It'd be kind of a circular synthesis. But in this case, we can use either the nitro or the aniline as our directing groups, and then we can remove the nitrogen. And we can't even see that it was ever there, right? So that's pretty tricky, huh? All right, any questions on that one? All right, so let's just pick another one. Here's a second synthesis here on the bottom. Oops, I don't think this one's not necessarily as tricky, but there's more than one way that we could do this. All right, so how might we do this one? Yeah.
We nitrate it and then add the bromine and then turn nitro group into amine and then into ester and then aryl acid.
So nitrate it, nitro group, then, what did you say?
And brominate.
Then brominate.
And then turn the nitro group into amine, the amine into carbon nitrogen triple bond, and then carboxylic acid.
No. Good idea, but we don't have one of those. Oh, well, we can't make that directly into the carboxylic acid. That's not one of our reactions, but we did convert it into something else that we could convert into carboxylic acid. What was that? The what? The cyano group. The nitro. Oh, you said that. Oh, sorry, I missed that. Okay, so that would be one good way. Let's see if we can fit that in here. Okay, so the idea here is I'm not going to draw in all these reagents because they're all the same as what we've been doing. We're going to add a nitro group. I'll put it over here. Okay, then I should have put it on the other side just to be consistent. Plus it can't fit in there. Nitro group. Then we brominate, and because nitro is a meta-director, we put it there. NO2. Okay, so then we reduce, just like we did above, to the aniline. Then we convert the aniline, just like we did above, to the diazonium salt. Then we convert that with copper cyanide, I'm gonna have to do the squeeze job here. To the nitrile, like that. And then how do we convert the nitrile to the carboxylic acid? Water and acid, right? So this is just a hydrolysis. Remember, whenever we hydrolyze carboxylic acid derivatives, we make carboxylic acids. Okay, yeah, question?
So when we add the copper cyanide, do we have to worry much about a competing reaction with substitution of the bromine?
Okay, good question. So the question is, when we get to this point right here, we have this nitrogen here, and we have the bromine, or this diazonium compound, and the bromine. Will the copper cyanide compete with bromide as a leaving group? No, it won't do that at all. That only works with these diazonium salts. Okay? All right, so yeah, that was good. Huh?
So you're just saying like the diazonium, like the leaving group is a lot stronger than bromine is what you're saying?
Yeah, I think this leaving group is a lot better. Right? And I don't know, the copper with using copper and stuff in here, it makes me wonder if there's some other mechanism that's going on too. But yeah, it won't. If we could just use copper cyanide to displace a bromine, we probably would have learned that before. Right? So it won't compete on that. All right, any other ways that we could do this? Yeah.
Could you just put like an acyl group, then brominate, and then change to carboxylic acid?
Yeah, something like that. So, but do we have a way to... So the question is, okay, so let's do this. Do we have a way to convert an acyl group, yeah, kind of, indirectly I guess, acyl group to a carboxylic acid? Let's just try it here. Okay, so the suggestion was we're going to do Friedel-Crafts acylation. Let's just put a acyl group like this. It's a meta-director, right? So then we can use that to add the bromine. Okay, and so the question is, can we then convert the acyl group into the carboxylic acid? To get to here. So how do we do that last step, that last part? Yeah? Potassium permanganate? Well, it might do that. We can oxidize alkyl groups with that. And so I don't think we ever explicitly saw, just in the book, oxidizing a ketone, but it might be surprising if that's not along the oxidation pathway. Yeah, up there.
Zinc, mercury, hydrochloric acid, and then potassium.
Yeah, so that would be another way, would be if we couldn't do this, so maybe let's write just potassium permanganate with a question mark here. So it's better for us to kind of stick with what we've been learning. And so the other suggestion was that we could reduce the ketone to the alkyl group first and then just do the benzylic oxidation. And so that we could use the zinc amalgam and hydrochloric acid, I believe, right? And then, I'm just going to write that, and then followed by potassium permanganate, which does the benzylic oxidation. All right, so my question would be then, if we're going to use this potassium Well, no, yeah, we could do that. I do have another way. I think what we could actually do, I don't really have room to fit in here. What if we, we could just put an alkyl group, do the benzylic oxidation to a carboxylic acid. The carboxylic acid would be a meta-directing group and brominate directly. All right, I think that would be the fastest way. All right, but all of this other chemistry is good as well. It's not as good. All right. It's down just for fun practice. You can do it. Or we can just finish these on Monday and then do a little spectroscopy after that. Yeah. Okay, so I got those two if you want to think ahead. I got this one that's not aromatic chemistry. All right, so I'll see you guys on Monday.